Thank you, Nathan. Good morning to everybody. So I'm going to talk about a different type of a machine learning technique, similar in structure and form, but slightly different in implementation, called transfer learning. And you would have heard lots of talks on using data, developing models, implementing it for similar kind of situations without having to do so much of tests. But concrete is such a heterogeneous material that even when we think that we have a similar data set, when somebody uses a different different aggregates, or different types of curing, it's all going to be different. So the idea is to use technique that is slightly different, that can transfer what we learn from one domain to the other. So that's what I'm going to talk about. And the idea here is, if you have lots of training data sets and you make predictions, that's one thing. What happens if you have untrained data sets, and how do you make predictions for that? So that's one of the things that we're going to talk about. There's a large body of publications that you would have already known. If you look at the graph, you will see exponential growth of papers on machine learning in concrete over the last 3, 4, 5 years. But they all deal with, or most of them deal with, property predictions, optimization, etc. And unsurprisingly, when you have high quality data sets, those predictions become easier. Now, the question is, what happens when you don't have those high quality data sets, or you don't know much about the data sets? The labeling versus unlabeling debate that's going on in the data science community for much long. So the idea is that after training, traditional models are able to predict on untrained data sets with identical input ranges and relationships. You may be able to predict, but the predictions may not hold water. Generally, if you want to predict, you have to have identical input ranges and relationships. When concrete, like I said, where you have lots of different changes, sometimes you may have those changes which are relatively mundane and may not really affect. Sometimes those inputs are very highly variable. So I'll give you a very simple example as a way of showing how the method works, and then I'll show you two different complex applications that we have worked on. So, missing data, and anybody who has dealt with machine learning, I'm sure you would have plucked your hairs over missing data and missing data labels. Data goes missing. What do we do when data goes missing? Typically delete that whole row and say, forget it, I will use whatever data I have available, right? Easier, but then once you have thousands of data, deleting a few data columns is okay. But think about it, you spend 28 days to get the strength result for this particular specimen and you want to delete it. Anybody who has done stuff with concrete in the lab, I'm sure you would have felt a pain in doing it. So data deletion is not really something that we want to do. So now, can we do data augmentation to fill in the missing gaps? And if you look at machine learning literature, there are so many ways of doing it. Autoencoders, decision trees, surrogate splitting. You can see a whole family of methods to do it. And then all the statistics-based approaches, I think, the stochastic regression, nearest neighbor approaches. These are all biased estimates. All data that you augment are going to be biased in one way or the other. And the biggest problem, not a problem, biggest challenge with machine learning is, how do you identify between biased and unbiased estimates of what you're getting? You can do adversarial nets, generate traditional adversarial nets, the GANs, to create thousands of additional data points. Once you start creating, you will get a lot of data, but how do we validate it and how do we do it? And the other better way for people like us in concrete area is empirical relationships between variables that we know that we can test and verify a few. So transfer learning is that part where, if you're lost in the wilderness of neural networks hyperparameters, and I'm sure you would have done this if you have done neural network training, you have hyperparameters, you want to train them, you don't know what they are, there are plenty of them, you don't know how to validate them, you rely on your Python or S code to create something that is in line with what you want. But then once you have a data on something, or model on something that is reasonably nice on stuff that you know, how do we transfer it into a domain that we are not completely sure of, and we don't want to do thousands of experiments to get there? So that's the idea. So you use deep learning models, transfer the knowledge to a specific domain. So here is a simple example. Lots of neural network data that you use to identify whether it's a car or a truck or whatever, and then you use that pre-trained one to identify what the image is in an image thing. Image is a little more complicated stuff than data, and that's why I showed it. So what do we do in transfer learning? We are assuming that source and target data sets lie within similar domain in typical machine learning process. So the complexity depends on the output in the target data set and the similarity of the domain or the feature space. And I'll tell you what that is. So if you look at data set size versus data set similarity, you have all these four possibilities. Large data set, but different from pre-trained models data set. A problem, right? Because your data set is different from what it's been trained. Large data set and similar to pre-trained models data set, here is where your typical machine learning models will work relatively well. Quadrant 3, small data set and different from pre. This is the killer deal. Small data set, again, when you want to get concrete data, you're not going to get tremendous amounts of data like some computer science guy changing some parameters and generating through a large simulation something. And then, of course, small data sets similar to pre-trained models data set, okay, but there are some difference. So this is the biggest problem, and this is what we want to achieve, and I'll show you some of the ways to do it. And one way is called a domain expansion. So you have a certain domain for which you have a machine learning model that's predicted everything, but then suddenly you get a few data sets from a concrete with a different water cement ratio outside the range of what you have trained. I know 0.3 to 0.5, suddenly you get something with 0.25, ultra high performance concrete, for example, right? Or you get something with a completely different aggregate. I've been doing everything with a certain aggregate, now I get a bunch of recycled concrete aggregate data. Do I have enough confidence in how I predict? So one is domain expansion, the other is domain adaptation. Target output is different, but you can relate it to the source input. So again, trying to reiterate the idea that for concrete, more often than not, you carry out on only a limited range of tests. Again, domain adaptation. I do everything for strength. You know strength is related to durability, but is there a linear relationship between strength and durability? All types of durability that a machine learning model can learn from? Probably not. If I have a little limited data on durability, can I now extrapolate it? Expanding the applicable range of mixture proportions through machine learning, combines with data augmentation and transfer learning. That's what we are going to talk about, which allows prediction of material properties across a diverse range of inputs and types, and therefore helps us to tackle a wide variety of cross-property relationships. So just to give you a simple example, I'm showing you here 4 data sets. One is a data set with 1,030 records of concrete with all of those different inputs. There were 8 variables. I'm showing only 7 here. The second one is on recycled aggregate concrete with 13 different inputs. The prediction was elastic modulus. Here the prediction was strength. I have another data set with 228 labels predicting strength, but that has only 6 variables instead of 13. And then I have another data set of 104. Again, you see the shrinking amount of data as we come from 1 to 4 with prediction of both strength and elastic modulus with 6 variables. Now, D1 and D3 contain similar inputs and outputs. The range of some of those in D3 lie outside the range of in D1. So this is 1030. Lots of data that I can develop a good machine learning model from. But the rest are all, I don't have enough data. Can I learn from this? Or I'm going to ask somebody, okay, I don't have enough data. Give me another 500 data sets of your sample for me to learn. I don't think many people would sympathetically look at you if you ask for that, right? So is there a way that we can do it? Again, compromise in prediction accuracy? Absolutely. Everything is a compromise. But can you live with the compromise and can you understand something from the compromise? So that's a question. So here is what we have done. Again, general machine learning details. I'm not going to go through this in detail. I'm sure lots of other talks have talked about it. The framework, the methods to use, artificial neural networks, ensemble methods, a rectified linear unit for activation, training using backpropagation, coarse optimization of hyperparameters. Again, these are all things that your standard machine learning codes will do, will repeat it infinite number of times. But here are some of the distribution ranges that we have used for some of the ensemble methods with random forest and extra trees, some of those things that we had to tweak to get the right model. So let me show you some machine learning predictions here. Like you saw, the initial data, 1,000 plus samples with 8 inputs, fairly nice prediction. I truncated it into 7 inputs to make sure that all my data can be in the same domain. Not really bad. But with reduction in data, this is the 13 original inputs. I try to truncate to 7 inputs. I lose refinement. I lose my prediction efficiency a little bit, but this is a compromise that I have to live with. Now, I say that, look, I got strength from one model. I have another set of concrete. I don't do transfer learning. I just use that model to predict the strength of this. You see that? It's totally off. I use the one that I have elastic modulus and use the one to predict of something that I don't have elastic modulus data of. Again, totally off. Here is why you need transfer learning. Again, I'm not trying to create new data. I'm not trying to create new experiments. I'm trying to tweak what I have using a transfer learning framework. So what have I done? Again, dataset organization is very critical in all of those. So here is Pearson coefficients to show for data 1, dset, D1 and D2. 8 parameters here, 13 parameters here. Look at which one and the combination has the least relationship so that you can reduce your input so that you can control your size. And then what I'm doing is, this is a traditional machine learning model. I have a bunch of data on strength and mixed composition. I predict strength with a machine learning model. I have something with elastic modulus. I predict elastic modulus. Now what I'm doing is use this model that already predicts the strength and transfer it to a different data set that does not have strength prediction to predict the strength. You see that? So this one did not have any strength data. I'm predicting the strength of that if you want that. Similarly, this one has elastic modulus. That's a machine learning model. I'm transferring it to a data set that did not have elastic modulus to predict the elastic modulus. So now cross-property relationships start to become much more effective. How do I do it? I do it simply by transferring the layers to the new model and retraining it by considering weights, minimization of error in the weights. So this is called an inductive transfer learning. Transductive is a slightly more complicated because the domains are completely different. Inductive helps me use a more intuitive parameter approach. Why? Because I know there is some relationship between strength and elastic modulus, right? I can know empirically there is some relationship. And if I can collect those empirical relationships, I can make the model learn from those empirical relationships and add to my existing data to predict without doing any new experiments. So this is the parameters transfer architecture that we have used. And here is a set of lots of empirical data. Now, if I'm using empirical data, I should not be using one empirical model and confusing the model saying that this is the ultimate truth, right? Now I want to give it as much of empirical data and let it learn exactly like your chat GPT or GPT-4. Give it the whole 9 yards of what you want and let it come up with what is a best outcome that you want. So give a whole set of empirical models to work with. This is data augmentation. Very careful data augmentation, not just random data augmentation, but careful data augmentation for transfer learning to learn the relationship between input and output using an already trained model. Right? So that's what we are doing. Again, changing the weights for backpropagation. Again, root mean square minimization of data. Source model acts as initialized weights and based on source data rather than the usual randomized weight. So when you do a machine learning model, you start with randomized weights and then you approach it. Now that will require a lot more trials, and then if the data is not from the same domain, the randomization might not work because it does not know what will work. Now you're confining that backpropagation using initialized weights from the model that you already have. So again, you're adding another few layers to an existing model to get here. And then with respect to target data sets, you do the objective function gradient, whichever way you want it. So here are two different ways of doing it, domain expansion and domain augmentation. I talked about here, this data set had some combination. The D3 did not have everything that went into D1 in terms of inputs. So that's a domain expansion. In this model, you look at elastic modulus of all of those, but it did not have strength data. So now that's domain adaptation. So adapt the domain or expand the domain. The algorithms are slightly different based on what you want. And then the advantage is once you have lots of data augmentation, once you've created lots of synthetic data, either using simulations or using empirical methods, now you can combine all of them and you say, okay, I don't really believe in my transfer learning. I don't know if this was right. You can run a traditional ML model and see if it's working. So now this is your final check. If all the combined data sets work well with a combined machine learning, traditional machine learning model, you know you have transferred it well, because now for everything you have a generalized model. So that's the approach. I'm just going to show you some very quick results. This is domain expansion. This is without transfer learning. You will see that lots of out-of-domain predictions, all these square ones without the shades are the out-of-domain predictions, which means those mixes did not belong to the original data set. But once you transfer learn them, and you change the weights and you adjust them, you can get very good predictions. So this is using dataset D1 for 1,000 samples to predict strength of the data set D3, which you did not have strength before, and you had a restricted data. Similarly, data augmentation with empirical models, which you can actually start to get very good predictions, and that is a strength elastic modulus prediction that you get after you have transfer learned. And if you look at ACI equations, Eurocode equations, they're fairly nice. Even your predictions work fairly nice with those standardized values. So just to show two applications. Combining data sets, because Nathan says there's not enough time, I'll skip that, but I'll show you a little more complex application. Now, data is fine. What about images? And so we've done this work with composites, where you have, again, for the time being, all the initial machine learning model is based on composites with circular inclusions, which means fiber reinforced composites, carbon fibers in an epoxy, for example. And so basically what we have is you can have different volume fractions, different distribution of fibers, different types of fibers, different matrices. You can't do all the testing, right? But you can do some testing, but you can actually do finite element analysis. You can do this parallel process. You can do 10,000 simulations, linear, nonlinear, depending on how much of computational power and how much of time you have. You do that, you get material behavior data. And you keep that entire data as your training data from all these simulations. Now you have synthetic data to train. You validate a few with that. Of course, your microstructure has principal component analysis that tells you if that's a microstructure that you want or not. But then once you have it, you can input unknown microstructures into it, feed with it. Now, even if you train with only this, what happens if there is size distribution of inclusions? Now, that's a transfer learning problem. What happens if the inclusion shape changes? Transfer learning problem. What happens if your matrix properties change dramatically from what you have trained? Transfer learning problem. So we have done all of these, and we have implemented this for aerospace composites. This was a work that was funded by NASA. But I can't show you too much of the new work on this, but I'll show you one more application, which is probably more exciting to people in the cement world, which we are looking at. Okay, this is the composite again, E22 and Poisson's ratio values from the models that is trained with different volume fractions of materials. You can get very nice relationship. Here is something else that we have done, where we have large data sets. So now you have lots of fly ash shortage, right? Everybody wants to dig the fly ash landfills to get fly ash. How many tests will you do? Will you do tests of every little point that you get? Can you do it? Can we predict something better? The idea is if all the fly ash, and there are cases where a certain power plant supplied a certain landfill over 30 years, and we have data of 10,000 data points of fly ash strength activity index and chemical composition from one power plant that went to one landfill, right? Now, you can nicely create a source model and predict strength activity index for this data. Now, if I take random samples, very few samples, either you take experimental measurements, either you take spectroscopic measurements, can we create a model and predict it so that somebody who goes and digs for the fly ash knows where to dig for the right type of fly ash, right? We have started some of this work. We are getting some very, very exciting results. And then it's a little more complex because we are doing a deep learning convolutional neural network to get all these convolutional neural networks. You see that regression here. I'm just showing deliberately a pretty bad regression because that's what we have now. I don't want you to be believing that, yeah, everything is hunky-dory and we can get all the very nice data. No, you will not, and you should not. So this is for regression problem. This is for classification problem. Does it satisfy 618? If I can classify it, and I need to do only the strength activity index only if it satisfies 618. If not, I don't even have to bother. Classify and then regress rather than regress and classify, because regression takes a lot more of compute power. Classification is much easier. Okay, quickly. I think I'm on time. So just wanted to show you a broad swath of transfer learning techniques to predict different properties of materials. We have used what's called an inductive parameter transfer learning. There is a transductive parameter transfer learning also, but which requires much more of understanding and compute power. But we have developed models to predict elastic modulus of a conventional concrete from mixture proportions and strength for a model for E that was developed and vice versa. And then we have shown that transfer learning can be used with an established ML model and trained with a smaller data set. Thank you very much, and I'll be happy to answer any questions if Nathan allows me to do it.
We have time for one question. So, can you go up to the mic, please, and also introduce yourself?
Hello, I'm Merstat from University of Virginia. So I have a question about transfer learning. So did you retrain the model?
Yes.
So you already have the output, right?
Yeah, well, we had the outputs, yes. We had the outputs, no. So for some cases, we have the outputs, which is the labeled output.
Okay.
For some, we don't have the output. That's where in the inductive transfer process, we used empirical relationships to have the first estimate of the output.
So you have two groups of...
Two groups of, yes, yes.